Good afternoon. Assalamualaikum. This is another part of the presentation on neural network applications, basically based on our general publications that we've done since 1996 and further on, using for simulated system and also online system, different types of neural network. This one, neural network for a partially simulated reactor sort of system. And basically it's being cooled outside, external cooler, and the reaction is simulated. It's not real reaction because it can be used for many reactions. We simulate it, and we are using the neural network IMC, internal model, inverse model as a controller, and the neural forward model as the forward model within the normal strategies that we've shown you for the IMC neural network based system. And this is online. We are in a real pilot plant set up, and this is a set point change, so we can see the system following the set point. They'll give a bit more time, but it's following the set point. And this is disturbance. When you have disturbance, it goes up and come back to the set point. A little bit of offset. And this is the actual temperature. This is the jacket temperature that we are using as manipulated. The jacket temperature is used to manipulate the temperature in the reactor system. So the jacket temperature also follows the set point that we set under some circumstances. So the actual temperature also follows roughly the actual temperature of the system. Okay, this is for disturbance using for the change of feed flow. And this is another one using neural network for batch system modeling and control, which I can be. And this is a batch system. So we are using here basically to estimate the heat loss in the system. There's a lot of heat loss in the system, basically the QR, and at the same time is implemented in the IMC strategy, favorite model just like before, and the inverse model as the controller. And you can see that you have the temperature set point and follows the temperature closely, set point. Okay, and these are the manipulated jacket set, and the also the for disturbance case. This is change in heat transfer coefficient. Heat transfer coefficient is an internal disturbance. So okay, so this is basically a system using neural network both as estimator, as a forward model, and as an inverse model controller. This one is using neural network in a model predictive method for steel pickling process. Okay. So basically we are trying to use a neural model within the optimize the manipulated output, and here we are controlling the concentration for using the neural network MPC control. Very good movement to the set point, and the PI control slightly slower when we compare. So we are controlling the concentration inside each of the bars. Okay, we control the concentration. Basically, we are controlling the pH as well using a neural network MPC based controller. This is a neural network used for controlling the dissolved oxygen in a sequencing batch reactor. Okay, and this is the sequencing batch reactor. Okay, so we are using the neural network to control the air being sent into the SVR, and so using the neural network inverse model state control strategy. So the airflow rate is being used as a manipulated variable, and we can see that we can track the output. Output is the dissolved oxygen content in the system, and also with noise. When put noise, just the real world is still able to track, even with noise, which is quite a huge disturbance in the system, but the neural network will be able still to track the set point even under noisy conditions. And so it's a real world is a noisy condition, so it's suitable for the real world application for both disturbance rejection and set point tracking. Finally, this is another work that we use neural network for polystyrene batch reactor using a neural network. Again, this is the neural network model being used in the optimizer, and trying to follow the track point. This is a bash system, so it's the set point is being tracked optimally, certain profile. So we track it certain profile, okay, and also compared with the PID, which some offsets, overshoots before it's tracking. This one is tracked from the beginning, it tracks straight the set point. So how robust, how fast the action of the neural network-based controller in the real world. So these are the different applications you can use neural network simulation and online. It's capable to control the system even under all these disturbances, noise, and non-linear systems. These are all non-linear systems basically. Linear systems, the PID should be able to control, but non-linear system, PID may have a little bit of offset, overshoot, slight mismatch, but neural network remove this huge overshoot, reduce the overshoot, reduce the difference, and so on. Of course, you have this noisy, this is the real world noisy, that doesn't matter. It's still able to track. The noise have not distracted it from its control strategy. There's a robustness test that we should do in all our simulations. So in your project, these are the things that you can some of the systems that you can choose using neural network or fuzzy logic, and some of the tests that you can do for set point, regulatory, and with some robustness, including noise, model mismatch, and so on. And later we'll have a demo slide using for neural network in MATLAB, different strategies where we can see how they can be done using MATLAB Simulink. But you need this basic theory and basic steps that I've given you to be able to design it properly, not just choose any neural network under the sun or black box way, but use the neural network or design a network based on the knowledge and the steps that we have given you. Then you will get a good robust neural network to be able to control your system in any condition that you put it. Of course, not too big a disturbance away from where it's being trained, or too big a set point change from what it has been designed. It may work, may not work, but within the constraints that you have designed it, within the constraints that you have trained it, within the constraints that it normally operates, it should be able to work. And within the operating conditions that it has been identified with, not extrapolate totally big, totally out of its range, which any controller may also have problem. But within the range it has been designed and built, it should be able to do it well and do a good job.